HAL Ecosystems bi-weekly meeting. Today is January 19th, and we're going to go over some of the updates from the last couple weeks. All right, so the TLDR, for SJDev 2, we have a little update. So the CAN bus driver is currently in review. I need to get to that sooner than later. Finally got it working well, and even working well for working well against a testing device that we just bought. I should have listed it here. Honestly, I think that would have been useful. But there's some really cheap USB to CAN converters out there, like, or like modules that you can like play with and like do a lot of testing with. And I think that that might be like the de facto thing we use. But I think also coming with that test fixture that we came up with before would still be the ultimate best solution here. We're gonna go over some updates to the CAN API. I put a little CAN here. We're gonna go over floating point mathematics. And we're gonna go over the percent. So we're gonna go in floating point mathematics and like the costs and like kind of a new feeling about it. The percent class as well as the frequency class. Okay, so let's get started. So with the update to the CAN API. So as Matt was working on the CAN bus driver, one of the things that we realized is that like some aspects of the CAN bus driver just don't make sense. For example, well, actually, I'll kind of describe it here. So we're getting rid of the attach interrupt, and it's been changed to the signature in there inside of it is no longer going to be taking a CAN reference. Now it's going to be taking a message. Now the CAN reference is literally taking the object that is the whole CAN bus object and then passing it into itself or passing it into that handler so it can do whatever it needs. Maybe send a message, maybe receive, go through and start reading out messages. So that's been changed to just give you a message. The intention here is that you put in a handler and whenever a message comes in, it will supply that handler with that message. You can do something with that message at that point. And then the functions receive as well as has data will be removed. I'm gonna explain why in like right now. So why? The previous signature begs the question of who clears the interrupt handler and when. So before, when we passed in the CAN bus driver, what you actually needed to do for it to work properly is you needed to actually read off one of the elements. You need to take one of the messages off out of the registers and clear it. I think for the STM, I think you had to like, I think you just had to like, you had to hit a flag and that cleared the entire mailbox as they called it, or a queue. And then in LPC, you just read off all the data until they're all read out, and then that's how you clear it. The problem is, let's say you grab. Is it a Black Widow? Sorry, side note. I saw something in my window. I've lost track of where I was. Oh yeah. So the main issue is that like if whoever supplies that handler does not actually read off all the data out of the FIFO, that interrupt will continue to run forever and ever and ever. And he made the little mistake of like not adding in that particular like thing that like to basically call the receive from the CAN handler. But also, how the hell would he ever know? Like honestly, like there's no really reason why anyone should know that's what you need to do. And even if we make it very apparent, why not automate this away? Why give them or people or users a way to shoot themselves in the foot and cause them to make mistakes? So we have a couple options here. So we can just tell them again, like very, very clearly, you are required to read the buffer back out to get out of a loop. We can also say when the handler occurs, the user defined handler is called. Then when finished, all the messages are cleared. That way, if you ignore the messages, it's fine. You basically just have it all cleared out, but you still get control over and access to the CAN bus whole interface. So you're able to send and receive and do whatever else you need, like a self-test, something like that. And finally, we have pass messages to the handler, clear messages after usage. So you, for every, let's say you have like a queue of 3 messages, you put in the first one, give it to the handler, give another one to the handler, give another one to the handler, you're done. And then at that point, you should have gotten rid of all of your interrupts. And if there's any other way, anything else you need to do in order to clear interrupts, you can clear them out as after you've already supplied the handler with all your messages. That last one ends up being the solution we're going to go for. And the reason why is because this means that there's no obligation on the user to really do anything in particular, and it's more clear for the person developing the driver itself. I'm going to do a quick check to make sure that, okay, we're still on. Because sometimes Discord has just cut out on me and I just don't know for a while. Oh crap. Okay, I am streaming. Okay, cool. I didn't see like the little thing at the bottom that said that I'm streaming. Cool. All right. So yeah, so option C is preferred option when because it's no obligation on the user, and it's a lot easier for the developer to know. And then also, why remove the receive and has data interface? Well, with option C, when can the actual user, the main thread, or any other threads ever get an opportunity to run the receive function and get something? If you have a handler that always runs if you have a interrupt that always runs your handler every single time you get some data, there's never going to be a chance where that function does anything. So it's actually obsolete. Same thing with has data. You can't ever have data if you're never in a context where you can actually get that data. Or like you're never in a context where that data is valid. So, and even if you did, if there was an interrupt and then you had another interrupt that occurred, and then you use has data in order to see if there's any data, and you remove data from there, that's actually a race condition. Is a problem. And let's say you wanted that receive function back. Well, because you have an entire handler, you can do whatever you want. So you can pass in a handler that just takes the data and throws it into a buffer or into a queue. Then you can pull out the data later on. So if you ever wanted to develop it, like you needed that receive synchronous, like receive like get a message at a time through that versus through an interrupt. This is a way to make that happen. I think that's a big important thing about a lot of these APIs, that like you can take a very tiny interface and really expand it out to a whole variety of characteristics, and you can get a lot of capability out of just a small set of rules. So yeah, that's pretty much the CAN API updates. Any questions on like why we're doing this with CAN, stuff like that? Okay, moving on.
So this, I know this is libembeddedhal, but I missed a little bit of the beginning. Was there something like seriously wrong with the CAN stuff, or not really?
Are you talking about relative to the robotics team specifically?
Yeah.
No. You guys are still fine. Just like it's a bad design, but it's workable. Like literally, I could keep the receive function and has data function and still have this like attach interrupt function, and it would still work just as long as you don't call the APIs that don't make sense to be called. With libembeddedhal, with SJDev2, even though it passes in the CAN bus object, and like basically the CAN network class manager handles reading off the data. So data gets read off, things get cleared, you're good to go. It works really well on LPC. This is more of the problems that would happen when you're trying to build a CAN network or your own CAN network or whatever you're trying to do with the CAN bus. So for the most part, for robotics, you're fine. I'm not going to change the API for SJDev2 just because like I want to kind of keep it archived as it is versus trying to improve it to match libembeddedhal. But yeah, we realized after doing another driver that this particular API does not make sense, and it's actually confusing for any user really. Great question though.
Okay, thank you.
Any other questions? Okay. Moving on to floating point math. So, original plan for libembeddedhal was that we would stay away from floats for the most part, and that is still the case. But I kind of lightened myself up a little bit on this one. I think the project does not require to be so aggressively against them. They are slow in performance. Turning them on and using them does consume more power than not. They take up space, and those are pretty much the biggest problems with them. But they're not as bad as I expected. So, for example, at least when it comes to cost, I made a little basic program, compiled it for ARM, turned it to soft floating point. Let me get some water. To soft floating point, and tried out all the following. So, trying out just floats. All operations are 32-bit. Doing all operations, including plus, minus, multiply, divide. Multiply, divide. Oh my god, I cannot think right now. Oh yeah, comparisons greater than equal, greater than, less than, greater than equals to, so on and so forth. All the proper operations, and then conversions. Those are actually distinct. Actually, they behave a little differently depending on how you use them. Whereas all the other comparisons are around about the same. So this is using just floats only adds 1K to your binary. So that's actually not bad. That's actually pretty good. Honestly, it's not terrible. Using doubles, only doubles, brings you up just a little, like another maybe 500, a little bit around about 500, a little more than 500 more bytes. If you do doubles with 64-bit conversions, now you're at 16, it's like 1800, 1.8K. That's still not that bad. Then you go up to doubles and floats, and you're doing 32-bit conversions. Things jump up quite a bit. You can see that it's almost like 1K, a little less than 1K above where we were before. Now you have the two types. You're kind of combining them together, so that's what you're getting. And then, surprisingly enough, above this is when you use floats and you try to do 64-bit conversion. 64-bit conversion, the reason why I add so much is because you have to do a conversion from float to double, and then from double to 64-bit number. I don't know if that's actually necessary, like by the IEEE, or like if that's like a requirement, but that's something that libarm GCC's math emulation for FPUs or for floating point units does. So it costs around 3K. And then finally, it costs around like 3.2K. Actually, I think this might be slightly incorrect. I think this might be 3.5K, but I'm just gonna leave it there. This is the data I had before. I might update it later on. But for the most part, I don't think it does not go above 4K. So it's actually not the worst thing ever when it comes to the cost of floating point arithmetic. So if a user decided that they wanted to use that, like, I'm not gonna stop them anyway. They can do whatever they want. But if a driver in particular was like, hey, we want to have a driver, want it to like be usable for everyone else, and we have floats in there, if they can show a good claim to why floats were like the best solution for what they were doing, then yeah, they should use floats. Like there's no ifs, ands, or buts there. Just use floats and make your life easier and the code more ergonomic than using some weird fixed point stuff. But if they can prevent themselves from needing to use it, then they should. And actually, the next set of libraries should actually help with that. I'll go into that in a little bit. Before we go into that, I'm actually going to show the Seeger comparison benchmarks for different mathematical operations. So if you actually look at the disassembly, or like the symbols for a GCC built application for ARM none EABI, you'll see EABI. The E, if you didn't know this, is extended ABI standing for application binary interface. Not super important. But basically, when you see this is some sort of deep low API built into the compiler for the most part. That's why it also has the double underscores. Now, so for add, if we look at the actual, if we look at the actual amount of time taken, and I don't know what the units are. I believe this is in microseconds. I think it might be microseconds, or it might be microseconds. I don't remember, but at least we have a scale of things compared to each other. And GCC actually does a really good job. If you look at like some other variants, like the Seeger runtime environment and like some of their other implementations, like they have like their thing apparently is like the fastest, but actually no, it's not. 31 average, and what is this over here? 21. So it adds a little. GCC adds faster. Then you have sub. Then you have I don't know what R sub means. Multiply, divide, the different comparisons. Then you have for double mathematics, and you have the comparisons for that. You have the float conversions, and then you have the double conversions. And for the most part, most of this is actually fine. Like, isn't that worse off from each other? But you'll notice that like things jump up from like just a few whatever these. Let's assume that they're microseconds to like 458 microseconds or 478 microseconds. And to give some perspective to that, if you have an RTOS running, and this is actually taking up nearly 500 microseconds. Half of the time that you have, for double division, half of the time that you're spending in that task frame of 1 millisecond is that one division, just one of those divisions. So if you end up doing a whole bunch of floating point division throughout your code, that will take multiple context switches before you actually finish getting that work done. I don't think this is in Microseconds I think is more like in nanoseconds, but if it was at that kind of scale, it would be problematic to have that around or to be using that quite often. But I'm pretty sure this is all at nanoseconds actually. That would make a lot more sense since, yeah. And then another big one here that's very surprising that I didn't realize is the time it takes to do conversions. So floating to long values and unsigned long values can take a considerable amount of time to do and to perform. I think if I highlight these, I can kind of see them. Yeah, it's these two. So that's just one little thing. I think that was really interesting to find out. We ended up finding solutions that didn't require floats, but even if we required floats, I think like no other solution was really feasible or made a lot of sense. Then I think we would have been fine. We just have to kind of look at the amount of code size that we're bring it up to. Any questions on like the floating point math stuff that we went over?
A random question because I remember when you mentioned this in the Dev2 Discord.
Yeah.
And then I was looking around at robotics, and we were using like arctan on the ARM system. And arctan returns its type as a double, and then we cast it to a float.
Yeah. So
would that be a conversion, or what would that fall under?
Yeah. Let me see if there's actually a conversion between these. Yeah, float to double is this one here. So let's see how long that takes. I think it's super fast. Yeah, it's negative. I don't know how that's supposed to work. That was like an error of some sort. But yeah, it should be an extremely fast cast. The reason why is because, so what you do is from what I remember, you take the you basically just bit you take the mantissa and you just chop off the least significant bits. Because I believe the mantissa is like 7 decimal digits for like float, and I think it's like a pretty big number for decimal. Or maybe it's like 16 or 24 or something like that. I forget. But basically, you just cut off the extra bits and then shove it in. Same thing with like the exponent. You just cut off the lower bits and you shove them in. So it's actually a fast operation. So I wouldn't worry about it too much.
Okay, I was just curious. Thank you.
Yeah, no worries. And also, like, I'm saying that, like, like floats in general for like the library code it should be avoided. But I think in your application, I think in most applications, it's not super important. I have worked on projects where you need to be that kind of fine tuned because it's not DSP per se, but like, actually there's a lot of stuff that is acting like a DSP, honestly. So it was real time and being fast everywhere you possibly can, and also reducing the amount of power consumption to get operations done was really important. So that's why this kind of matters, and I want people to feel like they can develop with that in mind using our libraries, and if there's going to be any sort of like performance loss, it's on their side. But for your application, using floats and stuff like that is perfectly fine. I mean, as one last thing, which is you can do floating point arithmetic on an 8-bit processor, the Arduino, and like, although like that's not, you really kind of shouldn't, because it just really can't handle those kind of operations. It can still do them, and it's still relatively fast when you do them. Everyone kind of did that for their projects, for their trial projects. So yeah, it's fast enough in most cases. It's when you start to like really do a lot of number crunching and you need to be real quick. That's when this stuff really matters. Any other questions? Cool. All right, moving on. Percent class. All right, so this is the thing that I've been working on for like the last 2 weeks. Probably the frequency is the one I've worked on more, but like percent I've been spending a lot of time working with like recently. So percent class was designed to do the following things. Now, its main thing is to basically be a representation of a floating point number from -1 to 0 to 1. And this uses exclusively integer mathematics for its calculations. So it's kind of like a fixed point type value, except I'm using the entire domain of 2 to the 32 for a ratio from, or like a number, yeah, some arbitrary ratio from like 1 over 2, like 2.1 billion. So yeah, it also represents a duty cycle. It can also represent a duty cycle for PWM or a clock signal, like a clock signal for I2C. But the original purpose for the percent class, and I want to kind of explain this again because I think I didn't do the best job before when I was explaining full scale. The whole point was to erase the bit resolution of proportional numeric values of arbitrary bit widths. That's a mouthful, and it sounds kind of crazy, but the next part will explain what I'm kind of trying to get at here. So, explaining bullet C. Let's consider an ADC that has 8 bits. Let's consider another one that has 10 bits. We know, and we assume that like both of them are hooked up to 5 volts as a reference. That just means that like the maximum voltage that you can read on these things that like constitutes like the highest value you can have for 8 bits or highest value you can have for 10 bits is 5 volts. And they're both connected to the same analog input. This is just to make sure that, this is just so that like we know like, that these two ADCs will give us different values, different numeric values when we change the input voltage in this little example. So we all know that like, if you have an 8-bit number that it's 0 to 255, and if you have a 10-bit number, it's 0 to 1024. Now, let's say you have a voltage input that's 2.5 volts. What you'll read when you read off the 8-bit ADC is 127. What you'll read from the 10-bit ADC is 512. Now, notice that if you were reading these two values and you needed to do calculations with them, they're both completely different, and you would need to know what the bit resolution is, or at least what their maximum values are, in order to be able to do anything meaningful with them. But the interesting thing about both of these numbers is that like it doesn't matter which one we use, both of them mean the same thing, 50%. Whatever our voltage reference was, this number here is 50% of that. And that's the important part, is realizing that like what really matters here isn't the actual numbers. What really matters is what is the proportion of that value from the voltage reference down to whatever the actual voltage is compared to like 0 to 100%. Really, it's a percentage. And if the voltage signal is 1 volt, then you get 26. This is actually because it's rounding, because if you kind of move the this is actually am I wrong about that? No, I'm not wrong about that. Yeah. Or am I? I might be wrong about that one, actually. Hold up. Well, regardless, the main thing here is that like 1 volt out of 5 volts is 20%. This might actually not be 20%. No, this is not. This is actually 10%. That's incorrect. So this actually should be 204. And this one should be, so 10 would have been 25.5 plus that's 50. That's 51. 51. Should be about 51. This should come out as 51 properly. But the whole thing here is that this is 20%. And that's what we really want. We don't actually care. We want to know what the percentage of where we are with our voltage. We don't really care about the actual numbers. So the percent class allows you to represent a value from 0 to 1, 0 to 100%, without using any floating point arithmetic, so that you can basically very easily convert those 8-bit resolutions or those 8-bit ADC values into something that we can just throw around as a percentage value. And it does this very efficiently in order to make this conversion as simple as possible. And here I'm going to show you guys the API, which you guys can take a little look at what's here. And I think before we go into this, I just want to say that the size of the percent object is basically an int32. So on normal 32-bit systems, it's as simple as throwing around an int, honestly. So it's a very lightweight object. So we have a couple of interesting little functions here. One of them is called convert, and this is how you convert your ADC value into a value that you can actually use for as a percentage. It looks like this. I should have the ADC. No, I do not. That's the demo. I want the source code. You see what that looks like? It's as simple as this, actually. Oh boy, oh boy. I'm just gonna kill this now. So here we have ADC read. All we do is get a little bit manipulation. We extract the bits out of it, the 12 bits that are here, because this is actually just 12 bits. I'm not sure why it says error constant, but whatever. VS Code's being weird. And then once we actually grab the bits out of this thing, the lower 12 bits, all we have to do is pass that value into %convert and specify the number of bits that it is. And this will do the work of converting this number into a 32-bit scaled up number that represents a percentage. So that's one thing. You can also construct a percentage from a floating point number. If it's done if the input value is a constant, And this should be calculated at compile time, and you shouldn't have to worry about any floating point conversion stuff being brought into the code base. You can also assign it to a floating point number. This is not advised, but this is available if you want to. You can also convert it into a floating point number. And also, you can explicitly cast it using a static cast into float or double. But the most important thing about this thing are the multiply operators. This basically allows you to take an integer value and multiply it by a percent value, and that value gets scaled down. So if I had a number, this is right over here, 255, and I multiplied this by some percent, 0.5, this would become 127, effectively. I think it should, yeah, 127 actually. Or 128, one of those. But the main thing is that it'll become this. And the reason why is because this thing literally acts as if it was this number here, except it does it with integer mathematics. Yeah. I'm thinking about adding in a division operator, which would actually scale up the value. But I need to make sure that the semantics, like when that would actually be used, and if anyone comes across like an actual use case for it. But for now, I'm going to probably not have it, but that's something I'm considering. So that's the percentage class. And the idea is basically to, erase any information about the bit resolution, because that's not super important. At least not important from the driver's perspective. And actually, I'm going to hone in on that a little bit more. If you have a particular sensor, let's say it's like a distance sensor, and it takes an analog, it's supposed to like read an analog value. Yes, having a 8-bit ADC compared to a 10-bit ADC means that you'll have you'll be able to measure more accurately. But the algorithms and the code should all be exactly the same, and that's why percentage is important. Is that like we know that we're looking for proportionality between a high voltage and a low voltage. So there's really no need to like have any more bit information. It's not going to change how the particular driver is going to operate. And then another thing is that like some other updates to some other APIs probably should have included this too. Sorry about this. I've actually made a lot of changes to a lot of APIs to fit all this stuff. But a lot of these things have had some values changed. For example, everything now uses frequency, which I'll go in a sec. But another thing is also that PWM now takes percent as its input and returns a percent as well. So when you try to control it, you pass it in a percent value and it'll do what it needs to do. To go into more detail about how this could possibly work, we have to go to the next item. But any question about percent before I move on? Okay, right on. Next up, we have frequency class. This one is probably like this one was fun. This one was awesome. I think this is actually gonna make the code look a lot nicer and prevent a whole field of. Oh no, there's a mosquito in my room. Damn it. A whole set of. Okay, he's dead. A whole class of errors and issues, because a lot of people will do their math for calculating frequencies and time counts and voltage frequency dividers, like that, and they'll make mistakes. They'll make a whole load of mistakes. And this will actually, I'm certain this will actually help to reduce the amount of mistakes people make and make sure that the values are as close to what people desire as close as they can get to. So let's look at frequency class for a sec. Frequency class was designed to make timing-based register calculations easier for driver contributors and application developers. A unified library for handling frequency and time-based calculations accurately while utilizing integer math only, no FPU required whatsoever. The goal is kind of like libexbitset, is to prevent people from making errors, making sure that people also do things the correct way, and also getting rid of a whole category of redundant code. Like why have to do frequency division over and over and over again when you can have a class that does this for you? Now, if you just have two frequencies, like, I have 1 megahertz and I have 1 kilohertz, and you want to divide them, the number's 1,000 if you're looking for the amount of cycles in a megahertz signal. that constitutes a single cycle in a 1 kilohertz signal. So that part's easy, and the math isn't too crazy. Although as you get more different and interesting values for your as you get different and more interesting values, like there's rounding errors you have to consider. But for the most part, yeah. Let's click on this little API to take a look. And just get you guys the insights. Frequency basically only takes up about 2 integers. It's a little chunkier. It's so that we can have frequencies greater than 4.2 billion, and without having to do any type of weird, without having to lose bits on the other side by shifting the exponent, the exponent of this thing over. So that's just one thing. To give you an idea of some of why the inspiration for this, I actually want to go over to systic timer. And I want to go over to this new function called schedule. So last week, or last time, 2 weeks ago, we talked about how we switched out attach interrupt with schedule. And the idea here was that, like, you pass in a certain amount of time. You want to schedule, like, either that a particular thing is going to, how should I put this? You want to schedule an event to happen sometime in the future. Let's say it's 1 second. Let's say it's 1 minute. Let's say it's give me 1 sec. I just need to text someone back. Okay. Yeah, it could be a whole variety of numbers. It could be like 1 millisecond or 10 milliseconds. The main issue here was, well, how do we calculate the volts, the count divider? How do we know how many counts of a certain frequency will get you that particular time duration, at least approximately as close? And in order to simplify this down, I created this function called cycles per, which is this frequency, input frequency, cycles per this duration, and that gives you back the cycle count. And what this really does is simply run this equation: frequency times period times the ratio number and the ratio denominator equals your number of cycles. It's really just saying that if you multiply the frequency and the period together, you get the number of cycles in between. These units cancel out. But it does it all making sure that it keeps in mind that you can put in any arbitrary duration, like 1 minute or 2 or 1 second, something in seconds, minutes, hours, whatever, and make sure to do the arithmetic correctly. But it's somewhat short, but this is something that people can mess up quite often in their code. So this is something that is done here. So that's one thing, is that, like, now if you ever need to figure out the number of the register count for, what your input frequency is, and what your time delay is, you can just put it into this function and get the answer. A couple other ones: divider. So if you just want to divide 2 frequencies together, you can divide them against each other. You can. There's also an operator overload for division as well against other frequencies, and that returns back an integer. If you divide a frequency by a scalar, it's just a scalar. Same thing with multiplication. You can still multiply up and down. You can subtract a frequency and add a frequency. And then, we have the multiply by the duration, which gets you back the count, and then vice versa. So this is a way to be able to to make those calculations. But on top of this too, I don't want frequency just to be, just to handle, just that one use case of frequency to frequency and frequency to time period. I also want it to do things beyond this. My hopes is that this thing could be used for generating CAN bus information, generating clocks for some other third thing that's, like, very consistent. But specifically, another one is duty cycle. So here we have this thing called calculate duty cycle. Oops, daisy, forgot. I still forgot that I haven't fixed that yet. So we calculate duty cycle. I should do this. Calculate duty cycle. It takes actually, is that the one I want? A frequency in percent? Yes, I think so. One of these is the most generic one. I'm trying to remember which one it is. Oh, well, these should be constant expression as well. I should fix that. Let me just go over to it. So if I actually go to this I2C real quick, you'll see an example. So here, I'll show you how we do how we set up the duty cycle for the clock rate for the I2C driver. It should be right here. This is it. So what you do is you for LPC, there's this thing called internal clock. So use the clock object. You ask it for, hey, internal clock, return back to me an object representing this peripheral that I'm currently running as, is I2C 0, 1, 2, or 3, or just 1, 2, and 3. Sorry, 0, 1, 2, 3. Doesn't matter. Actually, is there 3? Doesn't matter. Okay, so you get the frequency, which just returns back a frequency object. Then you run through calculate duty cycle. You supply it with the clock rate that your desired clock rate, and then you supply it with the duty cycle percentage. In this case, it's set by default to 50%. And then this splits it up for you. So this splits it up to, it gives you, like, you put the low count into the low count area, and you put the high count into the high count area, and that's it. So the idea is you just need to specify whatever your clock rate is, this needs to represent the clock rate of your driving clock rate. And this needs to represent where you want to, what your clock rate really needs to be. And this tells you what the proportion of the high and the low should be. Simple as that. I imagine this being used all the time in PWM generator code, because why do all the calculations yourself when you can just simply shove it through this thing and get your count high and lows? You may have to do some additional work on it to make sure that it fits. Or I can see some code where like you have to, like, you may have to do some modifications to the actual values to get the right thing. So yeah, that's pretty much that part of the class. And I think, is there anything else special that happens in here? I think that's pretty much it. Oh, cycles per second. So this is a way to get back, like, it just gets back to frequency. Cycles per second is just another way to say the frequency. That's pretty much what the frequency class does. And keep in mind that all this happens without any need for floating point arithmetic, because a lot of these are just integer division and things usually come out. Note that, like, we can't do frequencies lower than 1 hertz. So like if you have a frequency that's like, sub 1 second per pulse, yeah, we don't support that. And I don't think that really is a use case that almost anyone operates under. It's very rare for that. And if you really need time durations that are super long, that's where the you have an input frequency that's relatively large, and then you have the cycles per how many counts you need of that particular frequency to get the time that count you're looking for. So yeah, that's one little tidbit there. And yeah, that's pretty much everything. Let me actually, before I move on, before I stop it so we can have more discussion, not to sneeze, but any questions? Any questions about the frequency class or the percent class? Alrighty, let me stop the recording then.